Okay, let's talk about hashing. What I'm going to do, I'm going to go through the lecture notes that are posted already. Now, I have updated them just recently, so you might want to re-download those. But look on page 54, and I'm going to go through these and kind of use this as a guide. So it's good to start with, why do we even need this thing? Why hashing? Well, consider searching and sorting. All right. So if you have an array, just a simple, unsorted array, then your only choice to find anything is what we call a linear search, where you just look at every single item. So that's going to take big O of n, right? If you have a sorted array, then what you can do is a binary search, which is a little bit like a binary search in a tree, where you're subdividing the array in half, and then in half again, and then in half again until you find it. So this ends up taking big O of log n. All right? So log n is way better than n, but the price you pay for a binary search is that this requires that the data is sorted, right? And sorting routines, the ones that we've looked at, are big O of n squared and big O of n log n. So basically, if you want the advantage of a binary search, you have to spend the time up front to sort it first. And there's trade-offs depending on if you're going to do a lot of these, a lot of lookups or only a few lookups. And it just depends on what you're trying to get done. But there is quite a big of a cost here. N log n squared, n log n. What if I told you that for hashing, we could do things in big O of 1, okay? That is constant time for both an insertion into the storage area and a retrieval. This is way great, way better than any of these, right? In fact, it's so good, so much better. Big O of 1 is so much bigger than any of these other time complexities that makes you wonder why we even talk about these other time complexities. And, hashing, the answer is hashing can't do everything. It has limitations, and those limitations need to be fixed by methodology we've already looked at. So these other algorithms that we've already looked at that are more expensive, you still need those things. Anyway, so here's the basic idea. Let's start with something called direct addressing. So the idea with direct addressing is that the key becomes an index into the data store. So, basically, if your data were something like 5 and then a 3 and then a 7, and you had an array, if you were trying to find 5, you just go here and you've done it. So that's the basic idea. Well, keep in mind that there's other data that's associated with the key, which is the reason we're doing these lookups in the first place. Anyway, so let's consider a more real world type data, like Social Security numbers. Consider that. So let's say you had 555, 11, 1, 2, 3, 4, and then like 555, 22, like 5, 6, 7, 8, and a bunch more of these guys. How about 666, 44, 5, 5, 5, 5. Okay. So this is what? This is 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So what's the maximum, like we sometimes call that the key space, would be from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'd be from that to 9, 9, 9, 9, 9, 9, 9, 9, 9. So this is approximately it's 1 billion. But there's like 300 million Americans. So this is three times difference here. So you're wasting space. So like if you had an array here, and you started at 0, 0, 0, 0, 0, 0, 0, 0, 0 up to 9, 9, 9, 9, 9, 9, 9, 9, 9, and each one of these guys would go into a certain spot. You know, you're going to be wasting you're wasting you know, 3 times the space basically, right? There's going to be 3 times as many possible addresses. If this were just indexes in an array in RAM, there's 3 times as much possible space as there are possible keys. Okay, so we can be a little bit more sophisticated than that, right? We can do what's called address compression, right? Which is kind of the main part of hashing. So we could you could just, well, let's say we expect to have 100 people in our database. So we could start with 00 to 99, right? If we're expecting 100 people. And then we could just use any 2 digits in here to generate our index. So, you know, we could just use those. So we could go to location 11, and a lot of times you want to put the whole key in here, you know, so that you can check to make sure that you've got what you're looking for. And then this guy would go in location 34. Okay, and then so you know, to insert a piece of data, you would calculate the hash, which would be 11 for this guy, and then you'd go to location 11 in the array, and you'd find the key there. This is all key, but there'd be some other data, like maybe this was blood type or something. The reason that you're looking up this, maybe you want the blood type for all these people. All right, so this compresses the data range down from a billion down to however many you think you need. Okay, that's the basic idea of hashing. Now, what's the problem with this hash or data compression thing is basically the problem is collisions. Okay, like, you know, it's possible to have another guy that just happens to have the same last 2 digits, right? Then he's going to want to go in the same spot, and that's a collision. Okay, so we need a way to resolve the collisions. Okay, so hashing, to summarize, hashing is a way to avoid searching and sorting, which are expensive time complexity operations. But and hashing works by taking the key itself and using that to directly calculate a index into the data store. The problem with direct addressing is that the data store is often much bigger than is really needed. So we want some kind of a hash, which effectively takes the key value and uses part of the key value to generate an index into a smaller data store. That leads to the potential for collisions. All right, so how do we resolve these collisions? So that's where I'm going to kind of follow the notes a little bit more closely. So here I have this example where I have some keys that I've just made up: 25, 3, 35, 26, 13, 44. And I want to store these into a 7-element array. So that's this 7 here. Because the data store, I want to put these guys into a 7-element array. Because I'm anticipating that I'm going to have 7 customers in my database for my store or whatever. Okay, this is the data store. So, you come up with a hash algorithm. So this is H of the key. We call that a hash algorithm, or I like to say a hash formula, because it's just a constant time calculation. It's not really an elaborate algorithm. It just takes constant time. In this case, we're just doing a modulo. But even if we were doing a little bit more than just a modulo, that would still be independent of the number of elements. It's a constant time calculation. In this case, we're just taking the key and modding by 7. So 35 mod 7 is 5 times 7 is 35, right? I think. So the remainder is 0. And 6 times 7 is 42. 36, 37, 38, 39, 44. Yeah, 42. So the remainder is 2. And 7 goes into 3 0 times with the remainder of 3, right? And 7 goes into 25 3 times, right? Because that's 21. 3 times 7 is 21, and the remainder is 4. So like that, you calculate these. This is the data store right here. These are the indexes. Okay, like 25 modulo 7 is 4. So the 25 goes here. I was starting to rewrite the data store, but this is the data store right here. And this is just a table over here of keys and their hashes. So what you do is you start with some keys, and you generate the hash, and then that hash becomes an index into the data store. So 3 modulo 7 is 3, so the 3 goes in location 3, index 3 in the data store. 35 modulo 7 is 0, so 35 goes in location 0 in the data store. So now, the way it works is if element number 26 comes along, some guy with an index, or some guy with a key of 26, that's their identification, their key is 26. You modulo by 7, it gives you a 5, and then you go directly to the index 5 in the data array, and there's your location. So that's the basic idea with just some numbers. In real life, these would be something like social security numbers, or some other, it could be your phone number, or some other, your driver's license number, some other identifying piece of information. Could be a part number or something. So it's possible for collisions to occur, right? So here's an example of a way to resolve collisions. So I've got these key values, just sort of random keys that might show up, and I'm using this same hash algorithm. I'm just moduloing by the size of the data store, right? There's 7 elements in the data store, so they have indexes 0 through 6. And I chose some values that'll have collisions on purpose. So 25 mod 7 is 4. So you go here and you go to location 4 and you put 25 in there. Okay, then 39 mod 7 is also 4. So you go to the location 4 and you look and you see that 25 is already there. So you gotta put 39 somewhere. So one way to do it is just start stacking them, right? Just start chaining them together. And if you imagine if you were using a little data structure like this, you could do that, right? You could have a data array that has a key and then a pointer, right? So you could put the 25 there first, and then when 39 comes along, you try to put him here, but there's already somebody there. So you you initialize another node and set the pointer to point to that new node. You're basically building a linked list off of this array. So you could do that. Let's just continue. So 35 mod 7 is 0. You go to location 0, you put the 35 there. Then 14 mod 0 is, 13 mod 7 is 0, so you go to location 0, and 35 is already there, so you start chaining. So the order that the keys are showing up, the order that the keys are listed here is the order that they're showing up in. That's important. The order that these things show up sort of determines how the data is going to look in the data store. Okay, so you could do that. You could resolve collisions by just chaining together the data. That's one way to handle it, but you need to get into dynamic memory here. Maybe you don't want to do that for some reason or another. So another way to do it is rehash. Okay, so it's kind of a generalized term, rehashing. There's several different kinds of rehashing. We're going to look at linear rehashing, generalized linear rehashing, pseudo-random hashing, and quadratic hashing. So linear rehashing, you're basically stepping by one. Or if you're mathematically inclined, and you want to see how that might look mathy-wise, first you start at h of the key. Then if that location is filled, you go to h of key plus 1. And if that location is filled, you go to h of key plus 2. And if that location is filled, you go to h of key plus 3. So you're basically stepping by one. So let's use these same order. So 25 shows up, you hash the 4, you go to location 4. Here, let me redo it. Zero, 1, 2, 3, 4, 5, 6. Okay, so 25 shows up, you go to location 4. The spot is empty, so you put the 25 here. That's what's shown down here in the data store. Then 39 shows up, he hashes using this same hash algorithm, h key mod 7. He hashes to 4. You go to location 4, there's somebody sitting there already. So you go to h key plus 1. You just step to 5 basically. And you look in the spot, nobody's there, so you put him there. Right? Then 35 shows up, hashes to 0, you go to location 0. There's nobody there, so you put him there. 26 shows up, hashes to location 5, you go to location 5, there's somebody there already, so you go to the next one, empty, so you put him there. The 26 goes here. 14 shows up, hashes to 0, you go to location 0, there's a 35 there, so you go to the next spot over, empty, so you put him there. And then 46 shows up, hashes to a 4, you go to this spot, the spot's taken, so you go to the next spot. It's taken, you go to the next spot. It's taken, you go to the next spot, and you need to roll around to 0, right? Then next spot, you finally find a spot, right? This is like going into a crowded theater and you just have to, go way, way down seats until you find a spot. Okay? So that's how you do it. Now, that was insertions. So the order that the data shows up determines what the data would look like in the storage array. Then when you do a lookup, you sort of follow a similar idea. Let's say we want to find 39 now. So we first thing we do is we hash the index, and that's 4. So we'll start at 4, and then we'll look, and this is not 39. So maybe he had to move. So we start looking. We just start walking down, stepping by 1, looking for this guy, and we find him right away. We find him here. And if we were looking for 46, you know, it would hash to 4. You'd start here. You'd go here. You'd go here. You'd go here. You'd go here. You go here. Finally, you find him. So you got to step a little ways, but you find him. But let's say you were looking for 10. Who's not here, right? So h of 10 would be 10 mod 7. It's going to be 3. So you'd go here, and it's empty. So 10's not there. What about if you were doing find of 9? So you'd go, h of 9 is 9 mod 7. It's going to be 2. You'd go to location 2. That's not a 9. But if 9 were there, he might have had to step. So you start stepping. And you get to a blank spot, and you don't find it. So 9's not there, right? Because, he would have taken that blank spot. Right? So you basically need a blank spot. Because when you're looking for people, you go into the array and then you start stepping down until you find them. And if there were no blank spots, you would step forever. So you have to maintain at least one blank spot to account for that. So that's the basic idea with stepping by 1. I'm not sure what else I could do. I'll do some other examples on another video. That's what I'll do. All right. So the problem with this is linear rehash problem is this. You start getting, like, if this were your data array, you're going to put somebody here. You're going to put somebody here, you're going to put somebody here. Eventually you'll get a collision in which you'll step and you'll put somebody, and then you might get another one and you'll put somebody. So over time you're going to start getting these clusters, right? So there's this clustering is the problem, where it's like a pile up on the freeway. Once you get a small crash on the freeway, it just gets worse, right? Just right around where these collisions are happening, it just starts to get really bad. So it'd be good if we could space out these clusters, right? So, or avoid clustering by spacing out the data. So that's this generalized linear rehashing, or stepping by some step size. So in this case, the step size is 3. It's kind of arbitrary what the step size is, but 3 is one you could use. So you would first go to the key location, and if that were full, you would step by some constant c, which in this case is 3. And if that was full, you would go to 2c, which is 6, and then you'd go to 3c, which is 9. So you're basically going 3, 6, 9. You're stepping by 3, 6, 9. Right, so using the same data sequence. Here, I'll redo this array. So 25 shows up, he hashes to 4, you put him here. 39 shows up, he hashes to 4, you put him, you try to put him here, but that's full, so you step by. So let's see, let me put 25, then 39 shows up. You try to put him here, but that's full, so you step by 1, 2, 3, and the 39 goes to 35. Where's 39? Oh, this is wrong, isn't it? $39 shows up. 1, 2, 39 should be here. So it looks like I got an error in here. This should be step size of 2 to match the data that I have. So let's see. So first 25 shows up, you put him at location 4. Then 39 shows up, you try to put him at location 4, but that's full, so you step by 2. So 39 would go here. Then 35 shows up, hashes to location 0, so they're just free, so you stick them in there. And then 26 shows up, you hash to 5, which is free, so you just stick them in here. And then 14 shows up, which hashes to 0. So that was, this was 35. Oh, stepped over. Then 14 shows up. You try to put him here, but that's full, so you step by 2, put him here. Then 46 shows up. 46 shows up. You try to put him at location 4, but that's full, so you step by 2. And then you step by 2 again. Should be over to here, and that's 46. All right. So this sort of spaces out the data. Like, you know, you're gonna try to put somebody somewhere, and then you're gonna kind of go down a ways and put somebody somewhere and down a way. So it kind of prevents these localized traffic jams that can build on themselves and get worse. Yeah. So another way to space out the data and avoid these traffic jams is pseudo-random rehashing. So there you generate a sequence of keys that vary with each step you take. So first you'll try h of key, then you'll try h of key plus some random pseudo-random number, right? If that doesn't work, you'll try h of key plus another pseudo-random number, and then another pseudo-random number. So these random numbers you have to be able to recreate them in the same sequence, right? Because when you do a lookup, you have to go back in here and try the same sequence to find to find the guy that you used to insert the guy. So that's why these are pseudo-random and not actual random. Okay, so if you would start here, and if that spot is full, you would, in this example, you'd go over here or over here. You'd go that way twice, and if that location were full, you'd go this way once. You'd step by once this way, and then if that location were full, you'd step by 3 this way. So the sequence is -2, 1, and then 3. So you have to have an algorithm that generates the same sequence of random numbers, pseudo-random numbers. You could do that. Another thing you could do is this quadratic rehashing. We're not gonna do that, but it is an option. So I'm just gonna skip that. What we are gonna do is this double hashing thing. This is where the step size, okay, the step size is also some kind of special hash. So should be a plus sign right here. So you just step by a special step size that's unique to the key. So you try the original location. If that's full, you step by some constant. Okay, and each key has its own constant because each key is generated by a second hash function, right? So you step by some constant. If that's full, you step again by that constant, and then again by that constant. And the constant is generated by a second hash function of the key. So each key gets its own constant. That is, each key gets its own step size. So here's our same data that I've been using for the last couple examples, and then this this is the first hash function, the same one, the H key modulo 6 thing. So you get these initial index values. They have collisions, right? I've got 3 4s that collide, and I've got the 2 zeros that collide. And so what you do is, for the ones that collide, you apply the second hash function to generate this constant, which is a step size. So here I'm doing, for H2 of key, I'm using key mod 6 plus 1. You want to add at least a 1, because if you just mod by something, you have the possibility of generating a 0 for a step size. And of course, stepping by 0 won't get you very far. So you got to add at least 1. So in this case, I'm modding by 6. 6 is not important. It could be any number, but you want to add at least a 1. So 39 mod 6 is yeah, I had to remember my multiplication table. So the hash algorithm that we're using is for the first one is key mod 7. So yeah, 39 mod 7 is 5 with the remainder of 4, because 39 mod 7, 7 times 7 is 35 with the remainder. So 35, you have 4 left over. So that's where this comes from. And then the second hash algorithm is key mod 6. So 39 mod 6 is, 6 goes into 39 6 times, which is 36, which leaves a remainder of 3, and then we're adding 1, so it's 4. So anyway, you got to do the arithmetic on these things. But look, the idea is you generate the initial indexes with one hash algorithm, and then you generate the step sizes with another algorithm, and then you use the unique step sizes to resolve collisions. So 25 hashes to 4, you go to location 4, it's empty, you put the 25 there. 39 hashes to 4, you go to the location 4, and it's full. This 25 is already there, so we need a step size. So we generate this step size using this second hash algorithm, and then we step by 4. So we'll start here with 39, and we'll go 1, 2, 3, 4, and put the 39 here. All right, then 35 comes along, hashes to 0, you go to location 0, it's empty, so you put 35 there. Then 26 shows up, you hash to 5, you go to location 5, and that's empty, so you put the 26 there. This was the 30, this is 30, what the heck? No, this is 35 right here. Then you go to what are we doing now? 14. 14 hashes to 0, so you try to go here with 14, but that's full, so you use the second algorithm to generate this step size, and you step by 3. 1, 2, 3. 14 goes here. Okay, then 46, the first hash algorithm, the mod 7 thing. Back over here, you get this 4. Then you go to location 4 with 46, and that 4 location is taken, so you generate the second hash, and you go 1, 2, 3, 4, 5, and the 46 rather goes here. Okay, that's the basic idea. Let me just try and summarize here. So you have a set of keys. You use some hash algorithm that generates an initial index, and then you got to think about how big the data store is, and that determines your modulo, right? If your data store is 7, it's going to have indexes 0 through 6. So you want to do something and then mod by 7. Here we're just taking the key itself and modding by 7. You try to go to an initial location. If that's full, you try other spots and you use different stepping arrangements to do that. You could step by 1. You could step by 1. You could step by 1. You could step by some other step size. You could do this pseudo random or quadratic, which we're not going to do. And then you could also do double hashing, where you generate a step size that's unique for each key. And all of these, you still have to maintain an empty spot so that when you're doing lookups later that if you reach an empty spot and you haven't found that element, then that element is not in the data store. Okay, that's the basis of hashing. So it's constant. It's big O of 1. The idea is there's not going to be very many collisions. You want to have enough empty space, enough, room for cream, basically. If this were like coffee, you want to have enough empty space so that you don't get very many collisions, right? So most of the time, you're going to calculate a hash. You're going to go directly in there and find the person, right? Either put him in there if it's the first time, or if you're doing a lookup, you'll calculate the hash and find him right away. And if you do have to resolve a collision, it won't be very many steps, ideally, right? If you get, cheap and you try and compress the data range, then you're going to have more collisions, and eventually you'll be just walking through the whole array, and it'll end up being big O of n. We don't want that. You want enough empty space so that the chance of a collision is rare. It's like traffic, right? If the road is, there's plenty of lanes on the freeway, everybody's going to get where they're going. There's plenty of space between cars. But as the traffic starts to get crammed up on the freeway, right, and there's not very much extra space, the chance of a collision increases. And then as you start getting collisions, they just build up, right? So you want to have a little bit of empty space in here. Okay, that's the basic idea. There's one more thing that we can do, right? And that's perfect hashing. Okay, so if you happen to know what your keys are ahead of time, okay, then it's possible to generate a hash algorithm such that there are no collisions. Think of it like a party, right? If you're inviting people to a party and you know who's coming, right? And you can assign seats at the table for all your guests. The reason you need to hash is you don't know when they're coming, or even if they're coming. But if they show up, you have a seat for them, right? There's not going to be any collisions because you've found locations for everybody. So that's the idea with perfect hashing. So I've added a little bit to this perfect hashing notes, but so here's the idea. Let's say we have these area codes here, 916, 209, 559, all them. I could generate a hash algorithm where I just add up the digits, right? 9 plus 1 plus 6 would give me 16. And then modulo by the size of the data store. So here I want to store this in a 10-element array. So I'll just add up, I'll add up the 9, the 1, and the 6, and I'll get a, what is that? 9 plus 1 plus 6 is 16. And then I'll modulo by 10, and that'll be 6. 10 goes into 16 once, so the remainder is 6. So that would be where I want to stick 916 in location 6. Okay, then I do that for all of these guys, and I would generate initial indexes, right? 209, 9 plus 2 is 11, mod 10 is 1. And likewise, down here, I generate a 9, an 8, a 4, and an 8. Okay, now I've got a collision. 503, 5 plus 3 is 8, so that 8 mod 10 is 8, and 8 plus 0 is 8, mod 10 is 8. So 503 and 800 generate the same index, so I need to resolve this. So that's where this G of comes into place. So I'm taking the first digit, the second digit, and the third digit, and using those as indexes into a lookup table, G. So this array here is a lookup table. Initially, just put in the indexes in here. So location 0 will have 0, location 1 will have 1, location 2 will have 2. So, 916 I'd look up a 9, I'd look up a 1, I'd look up a 6, I'd add up 9, 1, and 6, mod by 10, I'd get my 6. But for 503 and 800, I have to fix one of those, okay? And I could change the lookup for 5, or the lookup for 0, or the lookup for 3, or the lookup for 8. Now, what would be the best thing to do? Like if I change the 5 lookup, it's going to break this 559, and it's going to change this index. And if I could change 3, that would be fine because there's only 1 3 in all of this, so I could do anything I want to 3, and that's what I did. So I changed 3 to 2, so that 503 would be 5 plus 0 plus 2, which would mod to 7. Okay, so just by changing this one value in the lookup table from a 3 to a 2, I can change this 503 from an 8 to a 7. And now I have no collisions here, right? I have all unique indexes here. So the data would look like this in the store, right? 916 would be in location 6, 219 would be in location 1. Likewise, no collisions. And I want to do a lookup. I can go straight to this spot and look it up. I don't have to do any collision resolution. Okay, this only works on this set of keys. So this works if I know that this is going to be my only set of data. All right, one thing about this is I'm wasting some space here. I'm wasting 1, 2, 3, 4 elements because I just chose somewhat arbitrarily to use a 10-element array. Ideally, I only need a 6-element array because I only have 6 pieces of data. So that's the second example. By doing a little bit more work up front, I can resolve the collisions and still get my data to fit in a smaller array this time. It's just a little bit more work. So what you do is you generate this lookup table. You initially start with just 0 through 9 for the values. All right, just basically store the index as the data. Location 0 has 0, location 1 has 1, likewise 3 has 3. You calculate these initial hashes, and then you look to what you can resolve. And like here, 503 and 707 both hash to 2. I need to change at least one of those. Something is not right here. Let's see, 0, 1, I don't have a 2 at all. Where's this 800? Why is that 8? Yeah, this should be a 2. I'll fix this on the notes and repost it. But anyway, yeah, because we're not modding by 6 anymore. Yeah, we are. So this should be, why is that? This should be a, why is that a, yeah, this is a different, so let's see, 9 plus 1 plus 6, it's 16, but now we're modding by 6, so this goes in here. It's going to be, it's 4, right? Because 6 times 3 is 12 with a remainder of 4. Yeah, a couple of changes from last time. We're modding by 6 instead of 10. We're modding by 6 because the data storage is now 6. Yeah, so this 8 mod 6 is 2. Anyway, you generate these. Then this one, 503, will collide with 707 because 5 plus 3 is 8, mod 6 is 2, and 7 plus 7 is 14, mod 6 is 2. And so I got too many 2's, right? I got a 2, and a 2. So you need to change something. 3 is unique, right? This 3 value is the only 3 value in all of these numbers, so I can change 3 to anything I want. Likewise, 7 is unique. This guy has 2 7's, but nobody else has 7's. None of the other keys have 7, so I can do anything I want to 7, and I can do anything I want to 3. So if you add 1 to 3, in this lookup table, it'll be 5 plus 0 plus 3. 5 plus 0 plus 4, which is 5 plus 4 is 9, mod 6 is 3. Just increase this by 1 will increase the original hash by 1. Likewise, or not exactly likewise, but 7 plus 7 is 14. Initially that hashed to 2, but if we change this to 9, we'll get 9 plus 9, which is 18. 18 mod 6 is 0. Okay, so now we've got all unique, 0, 1, 2, 3, 4, 5, which fit into the data store like here. Okay, so it's a little bit harder to resolve the collisions if you have a smaller data space than if you had a little bit of room for cream. Similar to regular hashing, but this is perfect hashing where there are no collisions. Okay, I'll do a couple more shorter videos just with examples. Thanks.